Good evening, everybody. Let's get started. Welcome to the Math 266 Q&A session. I'm your host, Scott Surgeon. How are you all doing?
Not too bad, you?
I'm doing dandy.
Good, thanks.
Um, so this is just, again, like a chance to ask questions and watch some problems worked out. I am recording this, so it'll be available in a couple hours so you can review it later. And I know you guys are neck deep now in the big integrals. Are there any questions from them? You'd like to see one worked out from start to end?
Um, Section 6.4, problem number 3. It's the one with x to the fourth, e to the 5x dx.
Okay, I'm going
I
there
went
right now.
through it and I just got lost in the
Hold on, give me a second to catch up. Six four,
yep,
which one? Number.
number 3.
All right, give me a moment. X4. All right, let me copy it down. So 6 4, number 3. Now remember, yours may vary from mine a little bit because the coefficients are randomly chosen. I'm going to share my screen temporarily. So this is the problem right here, correct?
Yes.
All right, now in regards to using a table, the problem with this kind of integral is that you get another integral in a slightly reduced form, but you still have to work this out using this form. So it becomes nested. Instead, what we're going to do is I'll show you another way to do this. I think this was discussed in the ed discussions, but it's a good chance to go over it right now. So I'm going to go to my screen here. Um, Let me get that. All right. So this is an example of a nested integration by parts. And so there's a neat little trick called tabular. So IBP is integration by parts. And what you do, there's a couple ways to do this. I tend to do it vertically. That's the way I was taught. Take the term that is a polynomial and differentiate it all the way down to zero. Okay. And then integrate the other one. And what's going to happen here is you're going to get powers of eight. I don't know if they are. I'll write it down. So it's going to be 64 times 8. It's going to be 512. All right, so far so good. Any questions?
No,
Now it's
that
important.
works.
Take it down to zero. The reason you need to take it down to zero is that it tells you when to stop on the right side. Okay, we need this guy. And then what you're going to do is you're going to kind of do little diagonals like this, and you're going to multiply. You're going to do alternate the signs like that, and I'll do it over here. It gets a little lengthy, so let's just be careful. It's going to be x to the fourth over 8 e to the 8x minus, and then we're going to have 4 over 64, which is 1 over 16 x cubed e to the 8x. And then here we're going to have 12 over 512. You know what? I'm not going to bother reducing. I'm just going to leave them as they are. Then we're going to have negative 24 over 4096. And actually, I forgot the x squared, so I took that in there. And this is going to be negative 24 over 4096 with an x e to the 8x. And then this last guy is going to be plus 24, 32,768 e to the 8x. And I'll pause here You could, if you wanted to, factor out the e to the 8x. It makes it a little cleaner, but that's optional. So I'll pause here. Are there any questions on how I assembled that?
No, I like that way of doing it better. I tried to go through it the way they have in the get help, and it became a fractional mess for me, and I got lost in there, and I ended up with the wrong answer.
Well, yeah, it looks like we have no choice but to deal with fractions here, unfortunately. I'm a little lazy right now. I could reduce these if I wanted to, but I'm not going to.
No,
Um,
but I think turning it to the tabular, that makes it a lot easier because then I'm not trying to figure out the parentheses and the fractions. And
oh,
like I
yeah.
said, I just I'm sure I missed a parenthesis somewhere and that completely screwed me.
Yeah,
But
that's
this is a
easy to
lot
do.
cleaner.
Um, if the problem was not a definite integral, this would be your answer plus C. Since it
Yeah.
is a definite integral, we're just going to pop in 1 and 0. When you put in a 1, I'll go ahead and factor out the e to the 8. All the x's turn into 1, so you just have 1 over 8, take away 1 over 16, plus whatever these guys are. Now I would just get my calculator out and punch that in and get a number. So I'm not too concerned about reduced fractions. Now when you put in 0, everything drops out except for this last term.
Hmm.
And that becomes a 1. So you actually have a 24. So you have e to the 0, which is 1. So you actually have this guy, again, just kind of by itself. And that's your answer, whatever it is. So put it on a calculator or Desmos.
Okay.
Now on the test, you have Desmos. Okay. So you could
So
do
on the
that.
test, will you be able to put in a decimal value, or do you want to see it as
Well, in this case, it would necessarily have to be a decimal because e to the 8 is not it's not rational.
right? But do we need to figure out what the single fraction is, e to the eighth, or can we just put it all into the calculator and
You
say
know,
it's
to be honest with you, on a
52.5?
quick, if this has bounds on it, just you want me to do it, I'll do it. I'll go to Desmos. Give me a second here.
No, it's
Because I certainly don't mind taking advantage of opportunities when they pop up. So let me go to, let me share my screen. So the integral, so I got to bring up, so int, oops, come on, there we go. Int, lower bound is 0, upper bound is 1. It was x to the 4, e to the 8x, dx. Um, oh, doesn't give me a graph, it gives me the answer. Y'all see that?
mhm,
240.892. Now,
okay.
I hate to bring, I'll tell you right now on the exam, there aren't going to be any questions where you just have to, where you could do this, where you already have a definite. We're going to ask you questions that are more like when they're indefinite. And so let me stop sharing here. Um, we would ask you questions. Basically, you might get a question like this without the bounds. So we would want to see this answer.
Okay.
Okay, so this is kind of the main theme of this problem. Because if you have bounds, yeah, don't even bother. Just do it on your Desmos. But that kind of defeats the point. And I actually pointed that out to the other instructors too. You can blame me for that because I do want to see you guys work these things out.
Yes, but when we're done, we're gonna put everything into computers in the real world.
Right. Well, even so, somebody has to program this.
No, I
Computers
know.
don't
Playing
know
a little bit
nothing
of
when you
devil's
think about it.
advocate.
Actually, does anybody want to take an image of this? I'll keep it right there. Just you want to take a quick image of that? Are there any other questions on this particular one? Any step that you're wondering what I did?
Do you always start with the positive, or is it only if
Yes.
the equation starts off as positive? Like if it was a
Well,
negative equation, would you start with negative?
No, this little scheme right here on the left is always plus minus, etc. However, if you have negatives within the integrand that pop up, just let them pop up naturally. And whatever you get when you multiply. So if you had like a plus here, then maybe you had a minus here, that would become a minus. So you let the negatives happen without, I guess you could say naturally. And then this alternating scheme on the left comes in at the last. And of course you would handle any quick, whether, multiplications. All right. Any other questions on this one? So let's look at a case where we're going to do partial fractions. Let me dream up a good one here. I want to get, you know what, one of the questions that's been popping up in the discussions is when you have repeated roots. So let's do, how about x plus 4 to the third power times x squared plus 9. And then on the top, let's make it fun. How about 2x plus 3? What do you guys think about that one? All right. So on the bottom, it's a fifth degree polynomial. And because this expands out to a third degree, then you have a second degree here, and that makes a fifth degree. I'm not going to FOIL it out. Now, this actually right here, the x squared plus 9 is an irreducible quadratic. Also note that this x plus 4 has multiplicity 3. It actually appears 3 times. The way to handle it is to write it out as each factor once and then twice. And then in this case, we'll end up the third time. Okay, now really what's happening here, this is actually, you could actually write this out as a single thing. You could actually write it out as ax squared plus bx plus I should say ax plus 4 plus squared plus bx plus 4 plus c, but that gets real messy. That's why we do it this way. This way is actually pretty clean. And then we have x squared plus 9. Now this is a quadratic, so we have to account for the possibility you might have a linear numerator. Okay. All right. So now we're going to recompose. So this is the decomp. Now we're going to do the recomp. We're going to bring it all back together. So we're just going to blob the denominator all back together. The numerator, this a gets multiplied by 2 of the x plus 4s. This and plus the x squared plus 9. The b gets multiplied by 1 of the x plus 4s. And then the x squared plus 9. The c just gets multiplied by the x squared plus 9. And then the dx plus e, put them in parentheses, gets multiplied by the x plus 4 cubed. Okay. So far, so good. All right. I realize I may have dug myself into a hole here because I'm gonna have to work out some cubes. Um, you can sometimes find the A, B, C, D, and E by just choosing certain values for X. Unfortunately, this only works for a couple of cases. We're just going to do it the long way. I'll show you the long way. It's worth the time. So just kind of bear with me on this one. This x plus 4 is actually x squared plus 8x plus 16. Then we have the x squared plus 9. This with the b is actually going to, I'll go ahead and FOIL it right now. It's x cubed plus 4x squared plus 9x plus 36. I'll leave the c alone. Over here, oh my God, I can do it real quick. It's dx plus e. I'm going to go ahead and use, I know the cubic, it's going to be x cubed. It's going to be 3 times 4, which is 12x squared. And it's going to be 3 times 4 squared, which is 48x. And then this is going to be 4 cubed, which is, what is it, 64. Okay. Again, I apologize. I realize I made myself a toughie here. I'll pause for a moment. Any questions on what I'm doing here? I know it looks like a mess. Trust me, it actually is going to be pretty easy. It's not a bad problem. I'm going to have to do a couple more foils and then I'll have what I need. So again, just bear with me. Right here, I have x to the 4 plus 8x cubed plus 16x squared plus 9x squared plus 72x. And then 9 times 16 is, I think it's 144. I'll leave this alone for now. I'll leave that alone. Right here, I'm going to have to FOIL this out. Ugh. This is going to be dx to the 4th plus 12dx cubed plus 48dx squared plus 64dx. And then I have to move the e through. It's going to be ex cubed plus 12ex squared plus 48ex plus 64e. Now, again, I keep on saying, trust me, this is where it starts to get kind of fun. I have this massive fourth degree polynomial on top. And what I'm going to do is I'm going to start grouping terms according to their powers of x. And then I'll write C for constant. Okay. And what I'm going to do is I'm going to go through each of these terms. I have, now remember, an A gets multiplied by all of these guys. So I have an A, skip that, skip, and I have a D. Okay. In fact, I think what I'll do is I'll lightly cross them out. And then for the cubes, I have 8A, I have a B from here, I have a 12B and an E. We can go ahead and get rid of them. For the quadratics, the x squareds I have, that's 25x squared. So 25, a 4b, a c, I have a 48d, and I have a 12e. For the x's, we're going to get rid of these guys. I have 72a. I should have an a there. A 9b, 64d, and a 48e. And for the constants, I have a 144a, a 36b, a 9c. Those may not have any d's, and then I have a 64e. Okay. Yikes, right? Now we just compare this to the original numerator, which was 2x plus 3. Yeah, sorry about the blurriness. My camera focuses like on one part cleanly, and it's a cheap camera. Um, if I look at all of this junk here and I compare it to the original, I don't, in fact, these are going to be 0, 0, 0, and then this will be a 2, and this will be a 3. Okay. Yikes. Now, of course, I was going through this kind of quick. I hope I didn't make a mistake in here somewhere. You just got to be really, really careful. Okay, now this looks like a nightmare, but it's not because I'm going to allow you to use Desmos for the matrix. Okay, um, and so you'll have access to the matrix calculator in Desmos. I'm going to show you how to do that. So what you need to do right now is we need to create a system, and the system is going to look like this. It's actually going to, so I'll make columns. Then we have the constants. From here, I have a 1A, no B's, no C's, a D, nothing else. From here, I have an 8, a 1, no C's. I have a 12, a 1, and nothing, because that was a 0. For the third row, I have a 25 A's, a 4 B's, a C, 48 D's, 12 E's, and 0. Here I have 72, 9, no C's, 64, 48, and a 2. And here I have a 144, 36, 9, no D's, and 64 E's, and a 3. Okay. Okay. That is a system. That's a 4. This is a system. This is a 5 by 6 system. All right. Now, in the old days, this right here would probably take you a good hour to work out, but we're not going to do it that way. I'm going to go to Desmos. I'm going to go to the calculator one. So give me a second. I'm sorry, the matrix one. So I'm going to share my screen. All right. So I'm going to create a new matrix. I need 5 rows and 6 columns. I'm just going to pop the numbers in. I'm just going to read them off. It's going to be 1, 0, 0, 1, 0, 0, 8, 1, 0, 12, 1, 0, 25, 4, 1, 48, 12, 0, 72, 9, 0, 64, 48, 2, and then 144, 36, 9, 0, 64, 3. All right. And then I hit return just to enter it. And this is the beautiful part. I go RREF of A, and there's my answer. And I hit this little fraction thingy job. And right now I've got my numbers. Beautiful. And they're awful, but you know what? They're the answers. So A is 30, negative 30, I'm sorry, 41, 31, 25. B, I'll write this down, is 2 over 125. C is negative 1/5. D is negative 41, 31, 25. And E is 114, 31, 25. Now let me pause here. Does everybody see how I did that on Desmos? I entered the matrix and then I did RREF, that's row reduced echelon form. And then I hit this little icon on the right to give me fractions. Okay. All right. If you know what, just kind of compare what I have on the bottom here with the top here, because you can actually do the integration right now here. Because when you integrate this, it's just a times ln x plus 4. Okay. This is going to be a power rule. So let's go ahead and do it. If I were to do the integration, let me go ahead and just copy this. And what I'm going to do is I'm going to split this one into 2. Okay. This just becomes a times ln x plus 4. This will be a power rule. It's going to be a negative b of 1 over x plus 4. This is, oh, geez, I got to integrate. This is going to be, let's see, negative 2c. I'm going to write it just using, it's a little clumsy right now. So I had to do a power rule here. I should be by dividing by negative 2. Okay. Let me just double check that one. Yeah, that should be right. All right. This one turns out to be a natural log. It's going to be d over 2 ln of x squared plus 9 because I had to do a quick u to u. And then this one's actually an arctan. Okay. So this is the form that you get when you perform all the antiderivatives without, you don't actually have to calculate A, B, C, D, and E yet. You just get the formats. And then since we got A, B, C, D, and E figured out, then we pop them back into place. And since I've already got it going, I'll just do it. Drum roll. let's see, this one would be 2 over 125 x plus 4. This is c divided by 2, so it's be negative 1/10. And actually, this would be a plus, so plus, I don't even want to mess around with that. This would be negative 41. Well, I can do it. 6250. Um, and this lovely guy, um, 114, 3125. Oh, you know what? I left off the 1/3 when you get arctan. So that's going to be, I have to multiply by 3. So 9, 375 arctan x3 plus c. Yikes. Okay, I'll admit that one was a bit heavy. But you know what? This had a lot of good math in it because they had repeated linear roots. So I show you how to handle that. I had an irreducible quadratic. I got to show you how to use systems on the Desmos, and then you just kind of cleaned it up at the end. And I will be the first to admit I ran through that pretty quick. I may have made an arithmetic error along the way. I hope I didn't. Um, Boy, lots of questions, I imagine. Any questions on this one? I don't think you have anything this nasty. I mean, some of the questions you may see on the test would simply ask you what would be the form for the decomposition. So if you got something like this, it might give you like 3 or 4 options of which they vary just a tiny bit, you know? Yeah, let's go back to the Desmos matrix. I'm gonna go back to the share my screen. All right, so which part, um, which part were you wondering what I did? You may have to come in with your audio because I can't see this chat when I'm in this mode.
No, actually, that's perfect. I just kind of missed the orientation of the matrix in Desmos versus what you had on. I wasn't sure exactly how it was oriented. So now that I can see it, that's perfect.
Yeah, it's going to be all this. It's a 5-row, 6-column monstrosity. And yeah, so experiment with the matrix. It's kind of fun to play with. It's really easy to get used to, and but definitely experiment because I will absolutely allow this on the exam because I don't. This class is not how to solve systems. So any method you want to use to solve a system is fine with me. And Desmos really handles the big, uh, these monster 5 by 6 cases really nicely.
So we'll have access to the Desmos matrix graphing and the basic calculator thing.
Usually you just get the main graphing one with the matrix one because the main graphing one has all the features you would want to do anyway if you're trying to do arithmetic.
Right. Okay. Yeah.
So we just give you the two.
Perfect.
I'm going to stop the share. Is there any other questions on what you see there? Okay. This one involved a little bit of trig, but this was just kind of a form that you should know. Once you get, let me just kind of put this to the side. Anytime you get 1 over x squared plus a squared, that's going to be 1 over a arctan x over a plus c. That's just a form that you probably want to memorize. Um, the one, I don't know, does anybody want to see one where it's like, you have to make the actual substitution and like, x equals something sine theta? Are you guys okay with that? I mean, I can do it.
There's when we put the answers in, at least in when we're doing the homework, it's either right or wrong. Um, is the test going to be like that, or are we going to be able to get some kind of partial credit once we turn our notes in?
Um, I go through and I look at everybody's wrong answers and I make a judgment call. Um, if it's obvious, you had the right idea and you did the syntax error, let's say. Somebody will type in a capital X instead of lowercase x, or somebody will use a bracket instead of parenthesis. That kind of thing will mess up Desmos, not Desmos, Infinity. So I go through and I look at everybody's wrong answers and I make judgment decisions. I don't, I only look at your written work in cases of like extreme confusion. If your answer is wrong in affinity, like it's nowhere near the correct answer, I'm probably not going to grant partial credit. So you want to be on the right track to begin with. I can tell by looking if you're on the right track. You know, there's just a certain form these answers have. So I hope that helps.
Answers my question. I don't know that helps is accurate,
Well,
but
and
yes, it answers my question.
there was a case on ed discussions where somebody had gotten the right answer but had the wrong coefficient. In other words, it
That
was
was me.
contradicting itself. That was you? Okay.
Yeah.
Um, the way that affinity works, and this is actually true for any uh, graphing model system like Maple and the other big ones, it knows in quotes what the answer should be because that can easily be programmed. And then what it does is it takes what you type in and it actually compares their graphs. And if your graph and the expected correct graph match, then you get credit because you might type something in a different equivalent format that's correct. And so it'll just simply graph the two in its brain, I guess, and compare. And now what happens is you can get a situation where your graph differs by a tiny, tiny amount. And the threshold, you can actually, if you're within the threshold, you can still get full credit. And that's what happened to you. You had a wrong coefficient, but you
Hmm.
got full credit because the error was so insignificant. You know, if you were to graph the correct answer and what you typed in, you would probably not be able to tell the difference. So, yeah, again, I'm on the lookout for those. This is not unique to Infinity. This happens in all the systems I've used. And you just kind of get to know how they work and you kind of know what to look for. So, all I can say for you guys and for everybody's, just go into it, hope for the best, and then I'll take a look and try to fix things as I go through. Okay. You're not going to be cheated out of points if you obviously have the right answer.
Okay. Thank you.
If you have the wrong answer, then that's your problem. All right. Well, my brain's about fried. How are you guys doing?
Too bad. On a note other than integrals, which is probably what
Sure.
people are relieved of, on 6 point, I think it's 6.5, where it's doing all the approximation stuff, which that I think is, pretty straightforward, Riemann sums, all that good stuff.
Uh-huh.
But on the Edfinity homeworks, it started going into Suprema and like the second derivatives, Supremas and second derivatives to determine something else. I can't remember off the top of my head. I could
No,
probably bring one up
don't
for
worry
you.
about that.
Okay, and I was like, wow, that kind of caught me off guard. I like worked through it, but it was like that was
Let
a
me
little
take a look. I'm
strange.
looking at, I've
I
got
could probably
six
bring
five
it up and tell
up.
you.
Do you remember which question that might have been?
I could probably bring it up in about 15 seconds.
Did you see the word Suprema in the key when they give you the how to?
Uh, in the question, it referenced the least. Oh, what do they call it? They didn't say Suprema directly, but they meant it. So like the least greatest, or yeah, hang on, let me find it. Right, say something wrong.
As I'm scrolling through these, I'm not seeing the word pop up. Um, you need left and right rectangles, rectangles, trapezoids, midpoint.
Yeah, see, that's all good. It was something.
Um,
Oh, here we go. The least upper bound. So it says find the error bound for t of 20, which is like trapezoid, 20 trapezoids, without calculating t of n using the result that the error equals, this whole formula where m is the least upper bound for all absolute values
oh,
of the
I see.
second
It's number
derivatives
3,
of the
right?
function. Yeah. It was just like, well, there's just a lot of least upper bound for absolute values of the second derivative. And
No,
I
don't
was like,
even worry
man,
about
that's
that.
okay. Yeah, that kind of, I was like, that's
You know,
interesting.
this is like what you would see in grad school math.
Okay. Like I hadn't even thought about a least upper bound.
I'm looking at the question right now. First of all, you would never, oh my God, I would never have you guys do a 20 subdivision. You'd be there all day. Well, they give you a formula.
Right.
So they give you the formula without much explanation. I guess you're just supposed to just follow the formula. Yeah, you know what? Don't worry about this.
Okay. Yeah.
I
Was
think this
hoping that
kind
was the
of,
case.
this kind of questions, let me share the screen real quick because even though it's not going to be on the test, I'm going to go ahead and share the screen. Um, I'm looking at the solution because I'm curious what they did. Um, let's say you had this question here, 3e to the, actually, you can just work this out. Okay, first of all, you know, uh, this 3e to the negative x over 4 can actually be integrated. It's not that hard to do. This is just a u to u substitution. Then you pop the 9 and the 0 in and you're done. So nobody in the universe would ever do this with 20 trapezoids. All right. Now, if you had an integral, let's say it was like 3e to the negative x squared over 4, then you got a problem because that doesn't integrate easily. Well, it doesn't integrate at all. You don't, I should say it doesn't anti-differentiate into common forms. You can integrate any continuous function, but if it doesn't anti-differentiate, your only options then are to do it using these estimation methods. And at this point, um, you know, well, let's be honest. Let's say you had to do this. So I would do it on Excel. I would just create 20 rows or 21 rows from 0 to 20, and I would just work out the endpoints and let's see from 0 to 9. So you divide 9 by 20. Like it's ugly. Yeah, you would. Do you guys understand the kind of the point of estimation of using rectangles and trapezoids and shapes like that? If you do, then you've got the idea. One of the things about calculus is that you can differentiate any function no matter how complicated it is. Differentiation is completely algorithmic. On the other hand, anti-differentiation is not. And this is what you're learning right now. You're learning all sorts of clever tricks to anti-differentiate functions. But you know what? The vast majority of functions out there are not anti-differentiable. And so all the tricks in the world won't make them anti-differentiable. That means you cannot express it in normal elementary functions that you're used to seeing. So the integral of e to the negative x squared is a good example. That's used in statistics. The only way to do that is to do it numerically. And you would, by hand, you might do it using rectangles or trapezoids. Or in this day and age, you do it on Desmos. But then what is Desmos doing? It's doing basically lots of narrow rectangles. So really integration is like adding infinitely many small terms. And if you understand that, then that's kind of the idea that we're trying to convey here. I hope that makes sense. All right, we got 15 minutes. Let's see, let me bring up Desmos. I've got, or Infinity. I keep on getting them backwards. So 6-1 was basically, what was 6-1? Integration by parts. All right, you guys comfortable with that? 6-2 is sines and cosines and variations. And then 6-3 would be the partial fractions. And 6-5, where's your trig subs? Maybe that's 6-2. Might have gone over it too fast. Yeah, it is. All right. This is probably the most difficult module of this class. And it's not so much that it's hard math, it's just that it's tedious. There's a lot of steps that you must do exactly right. There's so many opportunities to make a mistake that just one mistake can mess up the whole thing. And so if you're able to get through these reasonably well, you're probably going to be fine. The rest of the class is not nearly as intense as this module right now. I hope that helps you, keeps your spirits up. I do have time for one more if anybody wants to volunteer one.
Way longer than I needed to do it.
Yeah.
It's so it was a definite integral, but that's not really the hard part. It's the square root of x squared minus 1 all over x. And I got there in the end, but
All right.
I probably went a loop-de-loop around way I didn't need to go.
All right, well, let's go for it. Here's what I do. If you're going to memorize anything from trig, you really need to know the Pythagorean identity. And then you need to know the two corollaries. If I divide through by cosine squared, I get tan squared theta plus 1 is equal to secant squared. And if I move the 1 over, I get tan squared is equal to secant squared theta minus 1. And I look at the form that I have here. I have x squared minus 1. That matches up with this guy right here. So I'm going to use this form. And what I'm going to do is I'm going to let x be tan theta. Now, you get a little lucky here because that's a 1. So this will work. Now, if this was, say, a 4, I would have to have a 2 or whatever this is. This is an a. You have to have square root a there. So x is tan theta. That means dx is secant squared theta d theta. And what you do is you plug them all in. I'll just show you the steps. It's tan theta quantity squared minus 1 all over tan theta again. Then we have secant squared theta d theta. Okay. Let's see what we got here. Tan squared theta is secant. So you actually have secant squared theta, which is just secant because the square root and the square are canceled. So you have secant theta, you have tan theta, and then you have secant squared theta d theta. Now, nothing jumps out at me right here. So you know what I'm going to do? This is an old trick I used to use. Convert everything back into sines and cosines. Let's see what we got. So if I do that, I have 1 over cosine, sine over cosine, and then I have 1 over cosine squared. Oops. So the cosines cancel. That's cool. And I have, looks like I'm going to have a sine in the denominator and a cosine squared in the denominator. Now, does that help me at all? Let's see. No, I still like to get those in the numerator if I can. So I think but maybe, well, let me see. Huh. Um, Maybe that wasn't such a good idea. I'm kind of running up a dead end here. Let me just double check
Is
myself. Go
is
ahead.
tangent squared of theta minus 1, isn't that I thought
Oh my
tangent
God. You
squared
know
theta
what? I
plus one
blew.
was secant.
Oh, yeah, geez. You know what? I should be using secant.
Secant theta, yeah.
Oh, no wonder. Okay, guys, lesson learned. You know what? When you get into a total dead end, maybe that's a hint that you did it wrong, like I just did. So secant squared, I'm going to do this quick. So it's secant squared minus 1, and bottom is going to be secant squared. Then I have secant tan blong blong. Okay, we're in much better shape. This just becomes tan squared, so this is just tan. So I actually have tan squared theta d theta. All right, this is much, much better. Yeah, you're right. Thank you. This was totally a dead end for me. This was getting nowhere fast. Well, tan squared is, well, secant squared plus 1 or minus 1. So this just integrates, integral of secant squared is tan. And then this is just theta, integral of 1. And then that's nice. So then you go back to your original substitution, which was x was secant theta. And that means that if you use, so that means 1 over, it gets a little weird. That means cosine of theta is 1 over x. So if this is theta, cosine would be adjacent over hypotenuse. So this would have to be the opposite leg. So the tangent is going to be square root x squared minus 1. And then this is going to be, well, it'd be arcsecant of x. Because I have to solve for theta here. And the only way I can do that is just arcsecant it to the left side. Okay, my apologies. I made the error right here and I was just running with it. And sure enough, I hit the weeds. Yeah, I got nowhere fast. Thank you for pointing that out.
Okay.
This worked out a lot cleaner.
I see what I did. I got to the tangent squared theta d theta relatively quick, and then instead of identifying that that was secant squared theta minus 1, and that'd be way easier, I tried like 3 different methods, and I got there, but definitely not as simple as that. So
I
thank you. I
think
appreciate that.
yeah, I can see where you might be able to get that to work, but it looks like you're going to be doing integration by parts and stuff.
Yeah,
And
I did. Yeah, it was
I would say
not pretty.
one of the things you're learning as you go through this stuff is you're just really learning to really acquaint yourself with all your trig. And so you're getting a good dosage of just all the trig identities you had however many years ago, and now they're coming back. So it's a good chance to review all that. Ouch. All right. Well, there's your answer.
Thank you. I appreciate it.
No problem. All right. Um, any final questions or comments? We are toward the end here. All right. Did y'all get my announcement? The test has been moved back a day. Actually, starting at 2 days. I'm going to be in Tucson all day on Friday, and I won't have any chance to do anything on the computer. So I don't want to have you guys doing a test if I'm not at least being able to monitor it. So you get a free extra day. Is that cool? Um, and then I'll remind you all this week. I've got some. I'll be sending you all some stuff this week. Anyway, obviously as we get prepared. If I send it too early, I find that a lot of students just ignore it. So I try to send it maybe like 3 or 4 days ahead of time, and then it seems like it has more of an impact. All right. If there's no more questions, I'm going to go ahead and power down here. I'll have this. I'm going to get this up on the YouTube channel, and I'll send you all a link here, probably about an hour or two. So you guys have a good evening and good luck with your math. I'm going to go ahead and count down here. 5, 4, 3, 2, 1.